everyone, and welcome to another Stat 437 lecture video. In today's video, we are going to be taking a look at handling missing data when we're actually programming in R. So if you're given a data set that has missing values in it, and you want to analyze those data in R, how can we go about actually sort of implementing these methods that we were talking about in the last lecture? So how can we, deal with imputation or weighting or whatever else? So this video is actually going to take place over two parts, or I'm going to divide the content that I wanted to cover here into two different lectures. So in today's video, we're going to take a look at missingness when it's completely at random, when it's not at random, or when we're using likelihood-based techniques. And so what these all have in common is that they're actually fairly quick to go through. They don't involve anything new. We're just sort of going to take a look at the impacts of this. In the next lecture, we'll take a look at using imputation or weighting techniques, which involves sort of the introduction of a few new topics, and so we'll take a look at that there. Now, as always, when we're doing programming, all of this code's available on the course website, alongside the modified data sets that we're going to be taking a look at. So in today's video, instead of analyzing new data, what I've gone and done is taken a few of the old data sets that we had looked at previously, and I have added in missingness according to a known missingness mechanism for us to take a look at. And so the reason that I've done it this way is that by sort of imposing the missingness ourselves, we can actually know, are these data for sure missing at random? Are they for sure missing completely at random? Are they for sure not missing at random? And that way we can really clearly see the impacts of these different types of missingness. Now, in practice, of course, you're not going to artificially censor some of your data, and as a result, you're just going to be applying these techniques based on what seems to fit best in the real world. But I felt like this way you could take a look and see, what happens when we have these different types of missingness and really get a feel for that directly. So all of that data is available on the course website. If you're interested in how we actually generate this, I'm happy to have that conversation with you. But for now, we can open up R here, and we can begin. So the first data set that I want to take a look at is actually the seizures data set, the epilepsy data set that we would have looked at in lecture 16 when we were introducing generalized estimating equations. So this data, the seizuresfull.csv, is exactly the file that we've been working with before. So I'm going to load it in, and I'm also going to copy in some of the model fitting code that we had back in lecture 16. And so in particular, I'm going to copy in this code that's going to do our reshaping for us, right? So we're going to create the long data set. As a reminder, we have the different Y outcomes, which are counts of the number of seizures that occur during each week. And then we have the offsets, and the offsets are just the length of time for each of those weeks. And so we want to reshape this to be the long data frame. And then we had discussed in the previous lecture that the ID number 49 appeared to be an outlier, right? And so I'm going to just exclude that observation. And then we want to make sure that we order it, right? First by the ID and then by the time, right? And so we'll run that as well. And then we also defined this post variable. And so the idea with this post variable is that it took a value of 1 if they were post-treatment and a value of 0 otherwise. And so it's just the numeric indication of whether or not time is equal to 0. And the idea here is that we want to see, is there a difference pre versus post-treatment for the rate of seizures that are being experienced. And then we fit this model complete, which was using this geeglm. It included the offset for the log term, and then treatment interacting with the post variable, and then age interacting with the variable. Now, of course, to actually call this, we'll need to pull in the geepack library here, and I can build this model now, and we can see if we just take a look at, say, the summary of model complete, this is the model that we had fit previously on the exact same data. We have our coefficients here, we have our correlation structure, we're using the exchangeable correlation structure, and so on, okay? And so now what we can do is we can say, this is the model that we know we should be getting based on full data, full observations, no missingness at all. Okay, so what happens if there is some missingness observed? So in addition to this seizuresfull.csv file on the course website, you should also find a seizures MCAR file. Okay, so seizures MCAR is a data set that I have taken the full data and just made some of it missing completely at random. Right, and so when we were talking about missing completely at random data in the past, what we had said is that if it's missing completely at random, all of the methods that we've seen before still work. And we can use an available data, or we can use a complete case analysis, and that's all still going to be fine as long as it's truly missing completely at random. Right, and so I'll load this in. And I'm going to essentially steal the same code to reshape and sort this out. Right, so all of this stuff that was pulled out of lecture 16, I've gone ahead and prepared just to get the data to be exactly the same level. So we first want to actually pull the reshape function as well. So I'll pull that in. So we're reshaping this based on the exact same parameters, right? Because this seizures M data set, if I just take a look at it quickly, here, you can see it looks exactly like our seizures data set. So we have our ID, our treatment, the age, the 5 y variables, the 5 offset variables. The only difference is that a number of these y variables are NAs now. So those are missing values, right? So it looks exactly the same. So we can call the exact same reshape function. And then we're going to just filter out the 49th ID. We're going to order it so that it does not have the issues with the GE pack library. And then we're going to define this post variable. Okay. And now what we can do is we can define a similar model using MCAR. So we'll say it's the geeglm. We want to specify y with the offset of the log of the offset, plus we had treatment interacting with post, and we had age interacting with post. The family is Poisson. The data is going to be this seizures long M data set. The ID is given by our ID variable, capital ID, and the correlation structure we've said is exchangeable, right? So it's exactly the same model as up here, except we're plugging in the MCAR data set. Should be a lowercase m there. And so you can see that that model fit. Now, the prediction that we would have based on what we talked about with missing completely at random data is that this GEE-GLM function should fit exactly or close to exactly the same model. It'll be a little bit different because obviously we have a different subset of our data available to us, but that these parameter estimates should still be sort of valid. And so if you wanted to take a look at this, what we could do is we could say, let's take a look at the model complete summary. And if I just call coefficients here on the summary, you can see that I have a typo, coefficients. You can see that we get the table for the estimate with all of the p-values. And so I can do the same thing on the summary of the model MCAR, and we get the coefficients there as well. And if I expand this up, now what we're looking at is the model summary for the coefficients, the estimated coefficients when we have the full data, and the model summary when we have the missing completely at random data. Now, the first thing to note is that just a visual inspection of these estimates appears to be quite similar, right? So we have 1.87, 1.87. You know, we got negative 0.12, we have negative 0.12, and so on, right? Some of these are a little bit off. So this post variable, I mean, it would be negative 0.5 if you want to round to that, but it's a little bit off, but they're still fairly close, right? And this is true across all of the different parameter estimates. Now, we should expect that there would be slightly more variation in the MCAR data than there are in the complete data, and that's just because we have an effectively smaller sample size, right? So we should be less certain of anything. But that doesn't actually appear to be making any big difference in terms of our hypotheses test, right? So if you actually take a peek at these p-values here, you can see that they're fairly similar. They're at least on the same order of magnitude for all of the different tests, and nothing about our change or nothing about our hypothesis test is really going to change a whole lot, right? And so the idea here is that if you have missing completely at random data, we can actually just analyze it exactly as we would, and we're going to see relatively stable results. Now, there's no guarantee that your data are going to produce accurate estimates, right? This is true of any sample that you take, whether there's missingness or not. And we would prefer to be analyzing data that's completely there. But the point is, if you're certain it's missing completely at random, we don't need to do anything special. We literally just repeated this analysis, and the geeglm function handled it accordingly. Okay, so that's missing completely at random, and that's sort of the best that we can hope for. Now, on the flip side, the worst that we can hope for is not missing at random data. Okay, and so for this one, I've regenerated a set of the air pollution data. So we'll just make a comment here that we're now dealing with not missing at random. And the idea here is that I actually took this air pollution CSV file and I added in missingness that's not missing at random. And so you can see that we also have this NMAR version on the course website as well. So I'll load in both of those files, and then we're going to want to do a similar thing where we reshape them here. So this is the data that we analyzed in lecture number 21, in case you're wondering where we got these from. But the model that we had originally fit, and I'll copy and paste that in here, we take this log FEV1, which is our outcome. We fit it using the age, the log of the height, the baseline age, and the log of the baseline height. We're going to take our random effects terms to be the age grouped by ID. We will specify the null correlation, which is sort of the default. I can actually just remove that. We don't need it. We'll use maximum likelihood, though of course you can use restricted maximum likelihood if you're more interested in those nuisance parameters. And we have this air pollution data set. And now what I'm going to do is I'll come here, I'll copy and paste this model down, and all I'm going to do for now is change out this air pollution to be air pollution not missing at random. Now, the other thing is that we're going to need to pull in the correct library here. So that's NLME. And we have those data read in. So now we should be able to fit this model, and we should be able to fit the model for not missing at random as well. And you can see that we get this error down here. Okay. And the reason that we're getting this error here is because we actually have to sort of treat this a little bit differently than we did with the geeglm function. So when we're using this geeglm function, if it has NAs in the data, it just automatically omits those rows. For the LME function, we have to explicitly tell it to do this. So for instance, we could say that we want to do the subset where we do a complete cases of log FEV1, right? And so all this is going to do, it's just going to keep everyone that we have the full observations for, right? And so if we run that, we see that we get the model fit without any error. And what we can do is we can take a summary of our model 1. And in fact, I'm just going to pull out the t-table part of this, right? Again, for the LME objects, the t-table is going to give us essentially the same thing that coefficients gave us for our generalized estimating equations. And so this just gives us the estimates of all of our fixed effects as well as their p-values and such. And I can do summary model1.nmar. We can take the t-table here as well, and we can take a peek at this. And in particular, I want to draw attention to, let's just say the p-values. And so, in fact, instead of even outputting all of this, I'm just going to output the 1, 2, 3, 4, 5th row, or the 5th column, sorry. And so you can see that we get those p-values there, and we get the p-values here. And so this is just extracting that p-value column from each of those different models, right? And so the p-values for the intercept, those are roughly the same. We have, 1.2 times 10 to the negative 13 or 10 to the negative 14. That's just a 0 value, right? 10 to the negative 59 or negative 46 is just 0. This log height is literally found to be 0. Can't even numerically differentiate it. And we have to the negative 303rd power. So again, we have a 0. For the baseline age, we're, a little bit less significant. So we have 0.027 and 0.026. So those appear to agree quite well. And then we're into the interesting value here, which is the log of baseline height. We have 0.1325. So we had concluded in the past that this was actually not significant, right? It's not significant at a 5%. It's not significant at the 10% level. In our log of baseline height for the model that has this not missing at randomness in it, we actually would conclude that it's significant at a 5% level, right? We have 0.04 as the p-value here. And so what we would find is that if we had used just a complete case analysis on this not missing at random data, we would have actually come to different conclusions about this model. We would have said that the log of baseline height term is actually significantly different than 0, whereas we did not conclude the same thing in terms of our first model here. And you can see that the estimated values don't look that far off of one another, right? But it becomes really hard to sort of assess how that's going to impact the model when we have this missingness in it, okay? And so in particular, the missingness that was generated here actually did vary based on the baseline height for the individual, right? And so the I forget exactly how that model worked, but the taller they were at baseline, the more likely they were to be missing, which might not be super realistic for this study necessarily, but in the real world, it's quite often the case that not only are you going to have missingness that depends directly on our outcome, right, but also depending on these other factors, and they could interact in a way that makes it so that you sort of overemphasize certain patterns, right? Now, the other thing that I want to just point out with this is that if I just call a mean on the is NA, so is NA will just return a true or a false depending on whether the value is NA. And if I do, looking at which of these values are actually missing, right? So this is just going to tell us of all of our outcomes, which ones are NA, and if we take a mean, that's going to give us the proportion of missingness, right? And you can see that there's only 9.7% missingness here. About 10% of the data are missing. Now, what that sort of should indicate to you is that there doesn't have to be a lot of missingness in order for it to be a big problem, right? So there's only less than 10%. If you look at real life data sets, oftentimes you're going to see 20, 30, 40% missingness for certain outcomes. And that can become a really big problem if it's not handled correctly. Now, the downside is that when the data are not missing at random, there is no really easy way to handle this. It's going to take on sort of more complex modeling. You're going to have to rely on more heavy statistical techniques. There's not sort of a great way around that. But that doesn't mean that you should just ignore it. In fact, you should do the total opposite, right? And so I hope that this sort of example illustrates just how important it can be to consider the missingness in our outcomes. Okay. So the last example that I want to look at, and the one that we're going to spend the most time with, definitely, is the missing at random data. Okay. And so we'll just make a note that now we're missing at random. And so to clarify, the differences between missing completely at random, not missing at random, and missing at random. Well, missing completely at random doesn't have anything to do with the outcome as to whether or not the value is missing. When we say that we're not missing at random, we depend on the outcome, and in particular, we depend on values of the outcome that we did not observe, right? So the actual missing value was predictive as to whether or not the value would be missing. For missing at random, on the other hand, it depends on the outcome values, but it only depends on the outcome values that we did observe. Okay, and missing at random is far and away the most likely type of missingness to assume because it's something that we can handle, but that we have to do sort of a little bit of work to handle. And so it's going to be a fairly common assumption to be seen to made, and it's probably the assumption that is safest to make if you actually want to do an analysis that happens to have missing data. Okay, so the data set that we're looking at for this one is this TLC data set. And we looked at this back in lectures 3 and 8, right? And so we can read that in. And this was a study of the lead levels in the blood of children. And so once again, I'm just going to pull in code that we had run back in probably lecture 8 here, where we converted from TLC to TLC long, right? And then I'm just going to sort this as well. Okay. And then we have a corresponding data set that is missing at random, right? So again, TLC MAR.CSV, and I will reshape this. And then we can actually sorted as well. There we go. Right? And so now the question sort of becomes, what are we going to be doing with the modeling? So when we first looked at this data, this was back when we were doing linear marginal models using likelihood estimation. So through the GLS function, the generalized least squares function, right? And so we had fit this model complete right here. To recap, so we are using the GLS function, which is from the NLME package. The model uses W as the outcome, which is that actual the level of lead in the blood. We fit it with a factor for the weak variable, which is our time, and we interacted that with treatment, and treatment was either active or placebo. We take the TLC long. We assumed this sort of unstructured form for the correlation matrix, depending on the ID. The weights gives us the ability to define our variance. And so we just didn't specify that, but we specified a different value of the variance for each week, and then method maximum likelihood, right? And so we can actually fit that model here, and that will sort of give us our estimates here. And we could, of course, do the corresponding model where we plug in the missing at random data. So we'll call it model MAR, right? All of this is going to be the same, except instead of TLC long, we'll have TLC long underscore M. Okay. Now, once again, what you're seeing here is that the missingness leads to issues with this estimation. And so what we'll want to do is actually come down here and say subset equals complete cases W. Okay. And this is just going to keep the non-NA versions. All right. Now, we had talked about how missing at random data requires us to actually model it in some way in order for it to be valid. But one of the ways that we talked about that happening is through likelihood. Okay. And the generalized least squares, this GLS function, actually is a likelihood-based procedure under the assumption that we have the model correctly specified. So if you remember, back when we introduced these marginal models, we first introduced just the continuous linear case for the models. And when we did that, what we had said is assume that it's multivariate normal, right? And then we can use maximum likelihood to fit. And then we generalized that in the same way that you use GLMs. And from there, we saw the generalized estimating equations approach to estimating without the need for a distributional assumption. Okay? And from there, we saw GEEs that were fit on continuous data where we didn't actually need that normality assumption. But the key piece here is that when a marginal model is fit to continuous data and you have the variance and correlation correctly specified, so all of these model parameters are assumed to be correctly specified, then we've specified a full likelihood model. And we know that the GEE in complete data does not need this correlation or variance parameter to be correctly specified in order to consistently estimate the model parameters. We saw that those matrices don't actually need to be there in order for the M estimators to still be valid. However, in order for it to be considered a valid likelihood estimator, we do need all of those correctly specified. So the long-winded point here is that if we're willing to assume this unstructured correlation matrix based on the ID and that the variance only depends on the week, and if that's correct, and if this mean form is correct as well, then we've consistently estimated our values with this missing at random data here anyways, right? And so we could take a look and say a summary of the model complete, and I believe that we should be able to call the t-table on this. Yep. And then we could do a summary of the model MAR, and we could call the t-table on this. And we should see, if we do a quick inspection here, that we get relatively similar values, okay? And so, just going through, we have 0, 0, 0, 0, same thing up to here, and then we have 7.9 times 10 to the negative 1, okay? It's roughly the same. Another 0, and then, 1 and change to the power of 10, or times 10 to the power of negative 2. And so, roughly speaking, we have very similar estimates here. The actual values of the estimates differ a little bit, especially, coming down here, this 4.8, this 3.152, maybe those are different from one another, but probably not, just given based on sort of the significance thresholds, the signs are all the same. It looks fairly similar. And so if you were confident that this maximum likelihood estimate was valid, then because this is missing at random data, we know that this is valid and we sort of move on. However, if we weren't using a likelihood-based technique to do this, then we might be into troubles. And so the last thing that I want to do in today's lecture, before in the next time we'll see how we can use imputation and weighting, is I just want to show you that the geeglm function would have returned us a very similar model. And that's because it's essentially doing exactly the same thing. And so if I just come in here and I define a model complete GEE, and I say that this is going to be the GEE GLM, and we use the same mean form as what we had looked at before. So that's the factor of week interacting with treatment. We take the data to be TLC long, and we take the family here to be Gaussian, right? So that's specifying that this is going to be a Gaussian generalized marginal linear model. We take the ID to be ID, and we take the correlation structure to be unstructured, what we had specified before. Now, if I take a look at the summary of the model complete GEE, and I look at the coefficients here, okay, and then we take a look at the summary of the model complete, and we're looking at the t-table here, right, you can see that we actually get identical estimates. So the estimators for the parameter values are identical. The p-values appear to be slightly different, but again, we're saying this is 0. Something times 10 to the negative 131 is also 0 for all intents and purposes, right? And so it's not exactly the same, right? Because the actual process of fitting is slightly different in these two situations, but for all intents and purposes, these give us the same estimators, okay? And so what this means is that when you're using GEE, but you're using a Gaussian assumption and you're specifying the mean model, is that you can actually view that as a likelihood-based estimator that we had seen before, right? And we saw this when you were using linear regression in the standard case as well, where you can either assume normality or you don't have to, and you get the same estimators out of it. So the same thing is happening here. But the reason that this is interesting for us right now is that if we hadn't specified unstructured correlation, for instance, so if instead we had made the assumption that there was exchangeable correlation, or that there's compound symmetry, or those are the same, or that there's AR1, or whatever the case may be, then you might run into a situation where instead of this being sort of a valid likelihood estimator, you're looking at a GEE-GLM, which is not likelihood based, and therefore needs to have missing at random data accounted for. So if I had gone through and I had made an independence assumption, right? So we're assuming that all of the components are independent of one another. And if I come in here and I take a look at the model complete, where instead of it being complete, we're using the missing at random data. So instead of that being TLC long, we use TLC long M, right? And we just take a quick look at the summary for the model complete GEE, and we look at the t-table, no, coefficients there. And then we look at the same thing, except for the missing at random model. So we had seen that when we did this for where we didn't specify independence, where we specified this unstructured correlation, that we got very similar estimates. Now here, we take a peek, you can see that this is no longer the case. And in particular, I want to draw attention down to this last factor, right? Where the complete values, we get this 0.01. And in this case, we get this 0.1, right? So an order of magnitude larger of a p-value in the test of this significance. Now, it's an interaction term with a weak variable and our treatment, and so whether you'd want to drop that with keeping the other levels of the weak factor is questionable. But essentially what we're saying is that the hypothesis test has changed here. Now, again, whether we would actually make the independence assumption is sort of, besides the point, because the idea is that if you had been working with missing at random data, where we had used a GEE that was incorrectly specified, then you're into this position where you can no longer rely on the likelihood values in order for that to be sort of valid, right? And so in the next lecture, what we'll do is we'll take a look at how we could take this independence-based assumption and actually correct that using either weighting or imputation techniques. Now, these techniques are going to be a little bit more, they require a little bit more input from you in order to do them, and they're not going to be perfect. But they are sort of the most commonly used techniques for actually addressing the issues of missingness in the real world. And so they're super handy to use, to become familiar with, to sort of get your hands on. And so we'll start with this exact example here where we take these models exactly and then work from there. And hopefully doing that will give you a good sense of how to actually work with this data. So as always, if you have any questions about anything that we talked about in this lecture, please feel free to ask me. All of this code should be online along with all of the data sets that are relevant, and I will see all of you in the next lecture video.